All right, 1.3 is about limits at infinity and the end behavior of a function. End behavior is a term that you've probably heard before from previous math classes. And really, when we're describing the end behavior of a function, what we're describing is what happens as x gets really, really large in the positive direction, or really, really large in the negative direction. So as x increases or decreases without bound. And so we have a limit notation for that, right? So if you see something that says limit as x approaches positive infinity of f of x equals L, then what that means is that as x gets larger and larger, right, as x increases without bound, f of x gets closer and closer to L. And then similarly, if you see a notation that says limit as x approaches negative infinity of f of x equals L, then that means that as x decreases without bound, so as x gets larger and larger in the negative direction, as x decreases without bound, f of x gets closer and closer to L. Again, you can pause this and write down these definitions. But one thing that's really cool about this is that all of the limit laws that we discussed in the previous section, in section 1.2, they still apply to limits at infinity. So, for example, limit as x approaches infinity of x is just going to be infinity, right? Limit as x approaches negative infinity of x is going to be negative infinity, just like you would expect it to based on the limit laws in section 1.2. Right, so all of those things still apply. Another thing that I'll point out is that if f of x approaches some limit L as x gets really large or really small, then L is a horizontal asymptote of f. So graphically, it shows up as a horizontal asymptote. Okay? But anyway, this concept, right, these limits at infinity, they're called the end behavior of the function, right? So what I want to do is take you through several examples here. So we'll work out these examples on a sheet of paper over here. But let's calculate, just to get our feet wet. Did I spell that right? Calculate. Yep. Okay, so just to get our feet wet with limits at infinity, let's calculate some things. Let's calculate limit as x approaches infinity of 1 over x. So let's see if we can think this through. The idea is that we're thinking about plugging in larger and larger and larger values for x, and we're trying to see what happens to 1 over x. Well, so if you think about it, right, if you plug in 1, 1 over 1 is just 1. But if you plug in 2, you get 1/2, which is smaller. And if you plug in 10, you get 1/10, which is even smaller than that. And if you plug in 1 million, you get 1/1,000,000th, which is really tiny. In fact, this thing is getting closer and closer to 0. So we're going to say limit as x approaches infinity of 1 over x is just 0. Okay? Let's do limit as x approaches negative infinity of 1 over x. Now what's going to happen there? Well, as x approaches negative infinity, so we're going to plug in larger and larger negative values for x. So if I plug in like -1, I get -1. If I plug in -2, I get -1/2. Okay, so that's bigger. It's closer to 0, right? If I plug in -10, I get -1/10. That's even closer to 0. And if I plug in -1 billion, I get -1/1,000,000,000th, which is really close to 0. So this limit is also going to be equal to 0. Okay. Well, so let's make it maybe a little bit more interesting. Let's do limit as x approaches infinity of 5 over x squared. Now let's think about this. What's going to happen? As we let x get really large, like if I plug in 2, I'm going to get 5/4. If I plug in 10, I'm going to get 5/100ths, which is smaller, right? So it seems like this thing is also going to tend to 0 as x gets really large. What about same function, but this time as x goes to negative infinity? What happens to this thing? Well, as x goes to negative infinity, 5 over, well, whenever we square a negative value, we still get a positive value, right? But more importantly, as we plug in bigger and bigger negative values for x, this overall fraction is going to get smaller and smaller, and so this is also going to tend to 0. Okay, so that's the idea there. Let's do maybe a couple more. Let's do limit as x approaches infinity of x squared, and then we'll look at limit as x approaches negative infinity of x squared. Well, what's going to happen here? This isn't 1 over x squared anymore. This is just x squared. If we plug in bigger and bigger values for x, well, we're going to get bigger and bigger values, right? If I plug in 1, I get 1. If I plug in 2, I get 4. If I plug in 10, I get 100. And if I plug in 1,000, I get whatever 1 million, I guess. So it seems like this is going to go off to positive infinity. Okay? What if I plug in negative values? So if I plug in negative 1, well, negative 1 squared is still positive 1, right? If I plug in negative 2 squared is still positive 4. If I plug in negative 100, I would get positive 10,000. So I think this one is also going off to positive infinity. Okay? And notice that's because we're squaring the results. If we were, say, cubing the results, then limit as x approaches negative infinity of x cubed would be negative infinity, right? Okay, so this is how limits at infinity work for some of these kind of simple things. Now, the reason I'm making such a big deal of these simple things is because it turns out that the end behavior of a polynomial matches the end behavior of its highest degree term. Okay, and here's a proof of that fact, right? So the end behavior of an entire polynomial, it should be the same thing as just the end behavior of its first term, of its highest degree term. So, proof of that. So let's say that we're taking this limit as x approaches infinity of this polynomial here, right? So an x to the n, an minus 1, x to the n minus 1, and so forth, all the way down to a0. Well, we can factor out an x to the nth power. If we factor out an x to the nth power, what are we going to be left with? Well, here we're going to be left with just a to the n. Here, if we divide x to the n minus 1 by x to the n, we're going to get a to the n minus 1 over x, right? And so forth with every term. If we divide x by x to the n, we're going to get 1 over x to the n minus 1. And if we divide a0 by x to the n, of course, we're just going to get a0 over x to the n. Okay, great. Now, what can we do with this? Well, remember, all of the limit laws that we discussed in section 1.2, they still apply to limits at infinity. So, in particular, we can distribute this limit across this product, right? So limit as x approaches infinity of all this stuff is the same thing as limit as x approaches infinity of x to the n times limit as x approaches infinity of the other factor, right? Now, this piece right here is interesting. Limits also distribute across addition. So we can think about taking the limit of each of these terms individually. If I take the limit as x approaches infinity of a to the n, well, that's just going to be a to the n, right? That term is not dependent at all on x. So as x gets really large, it's not affected. It just stays the same. It's just a to the n power. So this is just going to be a to the n power. But now what about this term? Here we have a fixed number up here, a to the n, a sub n minus 1. So it might be like 17 or something, right? But it's just some fixed number up here. Meanwhile, x is going to get bigger and bigger and bigger and bigger. So this entire term is going to get really small. It's going to go down to 0. And so I'm going to just like write a little arrow through it and say this term goes down to 0. And if you think about it, the same thing is going to happen to every term in between. All of these terms are going to go down to 0 because they are all fixed numbers in the numerator. Meanwhile, the denominators are going to get unboundedly large, right? So that the fraction is going to get really, really small. It's all going to get close to 0. Which means this entire limit here is just going to be a sub n, right? So this whole thing is just a sub n. So the limit that we started with, it turns out to be the same thing as limit as x approaches infinity of x to the n times a sub n. Or in other words, we can distribute that back inside of the limit, right? We can put this a sub n right here, and we get limit as x approaches infinity of a sub n times x to the n. So the limit of our original big, huge polynomial turns out to be the same thing as the limit of just the first term. Okay. Now, don't get confused. This is only true of limits at infinity, right? This isn't true for something like the limit as x approaches 1, right? The same thing wouldn't work out because none of these things would go to 0 in that case, right? But for limits at infinity, this is absolutely true, right? The limit of this entire polynomial is just exactly the same thing as the limit of its highest degree term, right? Which if you've written the polynomial in descending order, that's going to be its first term. So I want to walk you through a couple examples of this. So we'll come back over here and work out a couple more examples. Let's do limit as x approaches negative infinity of 7x to the fifth minus 4x cubed plus 2x minus 9. Okay. Well, so as we discovered just a second ago, this is the same thing as the limit as x approaches negative infinity of just the highest degree term of this polynomial, which would be the 7x to the fifth. It's like the rest of it doesn't even matter, okay, when you're dealing with limits at infinity. And it's because, and that makes sense if you think about it, right? Because this term here, when you raise something to the fifth power, that's going to explode. It's going to explode so much faster than cubing something or raising it to the first power. So these terms are negligible when x is really, really large. These terms just don't even matter anymore. Okay, now if we think about x to the fifth power when x is a negative number, x to the fifth power, because the exponent is odd, you're going to get a negative number back out, right? Like if you think about negative 2 to the fifth power, right? It's like negative 2 times negative 2 is positive 4, times negative 2 is negative 8, times negative 2 is positive 16, times negative 2 is negative 32, right? So you raise something to an odd exponent, you raise a negative number to an odd exponent, you're going to get a negative number back out. And it's going to be much bigger than the number you started with, right? If x is getting really, really large in the negative direction. So this thing is going to shoot off to negative infinity for sure. Okay, this is just going to be negative infinity. Okay, and that's how you would do that one. Note that if we were taking the limit as x approaches positive infinity of the same thing, then we would get that and we would get that, right? Okay, let's look at another one. Let's do limit as x approaches negative infinity of negative 4x to the 8th plus 17x cubed minus 5x plus 1. Okay, go ahead and give the video a pause and see if you can work out the details on this one. Okay, so here's my solution. I know that this is going to be the same thing as limit as x approaches negative infinity of just that first term, negative 4x to the 8th. The rest of the terms don't even matter. Now, if I plug in negative infinity and raise it to the, well, not negative infinity, but if I plug in something really big that's negative, like negative 10,000, and I raise it to the 8th power, I'm going to get a positive answer out of that, right? But I'm going to be multiplying that positive answer by a negative 4. So overall, the answer is going to be negative, right? And the larger the value I plug in here, the larger the answer is going to get. So this thing's going to explode down to negative infinity. Now, note that on this one, if I change this so that x approaches positive infinity, this would still be negative infinity, right? Because again, if I plug in a really big positive number, like positive 1 million, and I raise that to the 8th power, I'm going to get some huge positive number. But then I'm going to multiply that by a negative 4. It's going to be a huge negative number. So it's going to explode down to negative infinity still. Okay, so that's how limits at infinity work for polynomials. It's really pretty straightforward. Okay, really the only thing you have to keep track of is the whether or not the degree is, or whether the degree is positive or negative, and the leading coefficient, whether it's positive or negative, but just think it through and you should be able to come up with the correct answer. For rational functions, it's a little trickier, but not too much trickier, right? It's really not that. It's really not too bad, right? Because since limits distribute across quotients, the end behavior of a rational function is the same as that of the ratio of the leading terms. So I'll show you what I mean by this. Again, feel free to give the video a pause to copy down this little note if you want. But let me give you an example of what I'm talking about. Okay, so let's do limit as x approaches infinity of 3x plus 5 over 6x minus 8. Okay, now usually I wouldn't show this much work, okay, but I want to show you what I meant by the previous comment, right? So limits distribute across quotients, so we can call this limit as x approaches infinity of 3x plus 5 over limit as x approaches infinity of 6x minus 8. So now these limits distribute across addition and subtraction. So really we can call this limit as x approaches infinity of 3x plus limit as x approaches infinity of 5 over limit as x approaches infinity of 6x minus limit as x approaches infinity of 8. Well, that actually doesn't really help us all that much, does it? You know what? I have a better idea. So, what we can do is divide through the numerator and denominator by x. Okay, that's what I'm going to do. So, if we divide the numerator and denominator by x, 3x divided by x is 3, 5 divided by x is 5 over x. 6x divided by x is 6, and 8 divided by x is 8 over x. Yeah, this is what I wanted. Now we can distribute the limit we get 3 plus 5 over x over limit as x approaches infinity of 6 minus 8 over x. And now, if you imagine plugging in a really big number, 3 is not going to be affected because 3 doesn't depend on x at all. But here, this fraction is going to go to 0, right? And same thing down here, this fraction is going to go to 0. You're just going to end up with 3 over 6, or in other words, 1/2. Okay, anyway, that's the long way to do the problem. But the note that we discussed is that the end behavior of a rational function is just the same as the ratio of the leading terms. So in other words, if I were to do this problem a different way, just using that fact, here's what we could say. We could say, well, the leading terms are 3x and 6x, so this limit is the same thing as the limit as x approaches infinity of the ratio of just the leading terms, 3x over 6x. And the x's will cancel, so this is just limit as x approaches infinity of 3 over 6, which, also cancels to 1/2. But this term doesn't even have an x in it, so as x gets really large, it doesn't care. It's just going to stay 1/2, right? So that's another way to do the same thing, and that way's a lot easier, I think. So let me give you a few more examples of this idea. So limit as x approaches infinity of 2x cubed minus 5x plus 1 over 3x cubed plus 6x squared minus 2, something like that. Again, this limit is just going to be the same thing as the limit of the ratio of the leading terms. So this is just going to be limit as x approaches infinity of 2x cubed over 3x cubed, and that's it, right? The leading terms cancel, or the x's cancel, and so this is just 2/3. Okay, and that's all there is to it. Let me give you another example where this time where the degrees don't match. So because here the degrees were the same, here the degrees were the same, but if the degrees are different, this still applies, right? Let's look at limit as x approaches infinity. Actually, let's do a negative infinity since we haven't done any negative infinities yet. So let's look at limit as x approaches negative infinity of 4x squared minus x over 2x cubed minus 5. So again, this limit is just going to be the same thing as the limit of the ratio of the leading terms. And again, just let me emphasize that this is only true for limits at infinity. This wouldn't be true of something like limit as x approaches -3, right? But because we're approaching negative infinity, it turns out that this is just the same thing as looking at the leading terms. Okay. So we can reduce this a little bit. This is going to be limit as x approaches negative infinity of 2 over x, right? This x squared will cancel 2 of these x's and leave 1 of them. This 2 will cancel 1 of those 2's and leave a 2, right? So here to here is just reducing. Now, if we think about what happens as x goes to negative infinity, as x goes to negative infinity, so as x gets really, really large in the negative direction, this is going to get really close to 0, right? Like if we plug in -10, this is -1/5. If we plug in -1 million, it's -1/500,000, right? But it's really, really close to 0. So this limit's just going to be 0. Okay, and one more for good measure. Let's do limit as x approaches, we'll do a positive infinity again, of 5x cubed minus 2x squared plus 1 over 1 minus 3x. This one's a little tricky because the ratio of the leading terms is not going to be 5x cubed over 1. It's going to be 5x cubed over -3x, right? You have to actually take the largest degree in the numerator and denominator. But Once you get beyond that, I think it's fairly straightforward. So this is going to be 5x cubed over negative 3x. This x will cancel one of those x's and leave two of them. So I think what we're going to have is limit as x approaches positive infinity of negative 5/3 x squared. Okay, now if we think about what's going to happen as x gets really large, x squared is going to get really large. But then when we multiply that by a negative, it's going to be a really large negative number. So that this limit should just be negative infinity. Okay, so that's how limits at infinity work for rational expressions. Let's do some more. Let's do some that have some radicals in them. Radicals can be a little bit tricky. So let's do another set of examples. You can hear my kids downstairs talking about how my dog is stinky. Well, anyway, so let's do limit as x approaches infinity of the square root of x squared plus 2 divided by 3x minus 6. Okay, so I might have to remind myself how this works exactly, but here's what I'm thinking. So this is not a rational function because you've got a radical in the numerator, right? And so the rules that we just talked about with the ratio of the largest term and stuff, it doesn't really apply here because you've got this square root going on around the top. But there are a couple of things that we could try out. One of the things that occurs to me is that if I divide the radicand in here by x squared, so in other words, if I factor out an x squared, then what I'm going to have left over, I think that limit will be 0, and well, it won't be 0 actually, it'll be 1. So let me show you what I'm thinking. Maybe it'll be easier if I just show you. So here's what I'm thinking. I'm thinking that I can rewrite this as the square root of x squared times 1 plus 2 over x squared, right? So I'm factoring out an x squared. Okay? And then, of course, the denominator is still 3x minus 6. The reason that I'm thinking it's a good idea to do that is because I can take the square root of x squared, right? The square root of x squared is going to be the absolute value of x. Right? So this is limit as x approaches infinity of absolute value of x times the square root of 1 plus 2 over x squared. Now, just a little detail. You might be wondering, well, why absolute value of x? Well, if you think about it, right, square root of x squared. If I plug in 2 for x, 2 squared is 4, and the square root of 4 is 2. So, square root of 2 squared is 2. On the other hand, if I plug in negative 2 squared is positive 4, and square root of positive 4 is positive 2. So in other words, square root of negative 2 squared is also positive 2. So if I plug in a positive number, I get a positive number out. If I plug in a negative number, I get the positive version of that number back out. The only operation that does that is absolute value, right? It's got to be absolute value of x. So square root of x squared is just the same thing as absolute value of x. That's just something that you should memorize. Okay, so square root of x squared is absolute value of x. Anyway, but now check this out. I'm looking for the limit as x approaches positive infinity, which means x is going to be a positive number. So I can drop the absolute values, right? Because x is going to be positive anyway. So what I really have then is limit as x approaches infinity of x times the square root of 1 plus 2 over x squared over 3x minus 6. Now you might be thinking, well, that's not very helpful, but actually it is, because check it out. You can distribute limits across products. And so I'm going to rewrite this now as limit as x approaches infinity of x over 3x minus 6 times limit as x approaches infinity of the square root of 1 plus 2 over x squared. Right? You see that? Like if I distribute, or if I factor out the limit, then I would have x over 3x minus 6 times square root of 1 plus 2 over x squared. When you multiply those two things together, you just multiply straight across. This is like over 1, I guess. So this part ends up in the numerator. Okay? Well, so that's nice, right? Because here I have a rational function. And I know that that limit's just going to be the same thing as the limit of the largest degree terms, the ratio of the largest degree terms. So it's going to be limit as x approaches infinity of x over 3x. It's like the 6 doesn't even matter, times limit as x approaches infinity of the square root of 1 plus 2 over x squared. And now if you're thinking about this term, this isn't bad either, because look, as x gets really large, 2 over x squared gets really small, right? We've seen this multiple times so far. This thing goes to 0. 1 plus 0 is just 1, and the square root of 1 is 1. So this is just limit as x approaches infinity of x over 3x times 1. Right? This whole limit is just 1. Okay? Now, here the x's will cancel. We get limit as x approaches infinity of 1/3 times 1. I don't need to write that again. Limit as x approaches infinity of 1/3 is, of course, just 1/3. So there you go, right? So that's that one. Now I want to go back and do the same problem, but let's take the limit as x approaches negative infinity, because that's when you'll see why it's important to consider the absolute value stuff. So same problem, but let's take the limit as x approaches negative infinity this time. And we'll work through all the nitty-gritty math a little bit quicker this time, since we've seen it already. Okay, this is going to be limit as x approaches negative infinity of absolute value of x times the square root of 1 plus 2 over x squared over 3x minus 6, right? We saw this already. But now what I want to point out to you is that if x is going to negative infinity, then absolute value of x, so then x is going to be a negative number, right? If you take the absolute value of a negative number, you get a positive number back. So another way that we could do that and drop the absolute value signs is to call this limit as x approaches negative infinity of negative x times the square root of 1 plus 2 over x squared over 3x minus 6. So let's think about this for a second, right? So up here, when we dropped the absolute values, we kept it a positive x. That's because x was going to be positive anyway. Here, when we dropped the absolute values, we kept it negative x. Well, that's because x was going to be a negative number. If we want this to be a positive output, then we need to take the negative of a negative number. That'll make this a positive output. Okay, so we take this to be negative x. Okay, from here everything else is the same, right? So I'm going to rewrite this as limit as x approaches infinity, negative infinity of negative x over 3x times the limit as x approaches negative infinity of the square root of 1 plus 2 over x squared. And now again, this thing's going to go to 0, which means this whole limit's just going to be 1. Here, the x's will cancel. We'll be left with a negative 1/3. So I think this limit's going to be negative 1/3. If you like, you can call it negative 1/3 times 1, right? Negative 1/3 times 1, which is just negative 1/3. Okay. So that's that one. Let me take you through another example with radicals. Let's do limit as x approaches infinity of the square root of x to the 6th plus 5 minus x cubed. This is an interesting thing, because if you imagine just plugging in infinity now, and when I say infinity, what I really mean is imagine plugging in a really, really large number, right? What are you going to get? Well, you're going to get, some really big number minus some really big number, which could lead you to believe that, maybe this is just 0. And maybe it is, but then again, maybe it's not. Like, maybe this thing grows just a little bit faster than this one, in which case you're not going to get 0, you're going to get some positive answer. And maybe that difference gets bigger and bigger and bigger the larger x gets, so that possibly this thing could be going off to positive infinity. Right? It's kind of hard to tell just by looking. So we need to do some kind of algebraic manipulation. I could start off trying to do what I did before, and that is I could try factoring out an x to the 6th. Let's see where that leads us. I have a feeling it's not going to lead us anywhere useful, but we'll try it. So we'd have square root of x to the 6th times 1 plus 5 over x to the 6th minus x cubed. Square root of x to the 6th would be absolute value of x cubed. And hey, if x is going off to positive infinity, then absolute values, we can just drop them, since x is going to be a positive number anyway. And for that matter, I can go ahead and factor out an x cubed, right? Oh, actually, this did turn out to be pretty helpful, because now we can distribute the limit across that product. Limit as x approaches infinity here, so this is going to go to 0, right? Oh, no, this isn't helpful. Okay, because then we get square root of 1, which is 1. 1 minus 1 is 0. So we get, and here we would get infinity. So what we would end up with is infinity times 0, which is really ambiguous, right? That doesn't help us. This is another indeterminate form, which we'll talk about later on this semester, but we're not sure what that's going to be. Yeah, I mean, you might think, well, isn't anything times 0 just 0? I mean, but that's not quite true when you're dealing with infinity, right? It's like this thing could be growing faster than this thing is shrinking, in which case you're not sure that you're going to get 0 necessarily. So, so yeah, this kind of led us into a dead end. Let's try something else. So that didn't work. Now here's another thing you can try. Whenever you're dealing with radicals, remember you can always try multiplying by the conjugate. That's sort of the trick that we like to use. Of course, when I say multiply by the conjugate, I mean you have to multiply by 1 so that you're not changing what the actual expression is. But we're going to multiply by a special form of 1, which is going to be square root x to the 6th plus 5 plus x cubed over square root x to the 6th plus 5 plus x cubed. And by the way, I'm thinking of this as being over 1. So when we multiply this original expression by the conjugate, we're really multiplying by 1 here, right? Well, what do we get? We're going to get limit as x approaches infinity. When I multiply these first two terms, the square roots just cancel, right? I'm going to get x to the 6th plus 5. When I multiply the outer term, I'm going to get x cubed times this radical, but then when I multiply the inner term, I'm going to get the negative x cubed times that radical, and those are just going to cancel, which is pretty nice. And finally, when I do the last terms, I'm going to get a negative x to the 3 plus 3 is 6. Ooh, that's very nice, right? Yeah, that's very nice. Okay, what about the denominator? What do I end up with there? Oh, well, I'm just multiplying the thing by 1, right? So I get square root x to the 6th plus 5 plus x cubed. So I'm going to get 5 over square root x to the 6th plus 5 plus x cubed. Okay, now if I think about plugging in a really big number, I'm going to get a really big number here, and I'm going to be adding a really big number to it. That's going to make an even bigger number. So when I plug in a really big number, the denominator is going to be huge. Meanwhile, the numerator is just fixed. It's just 5. So I'm going to have 5 over something really large. That's just going to be really close to 0. Okay? So multiplying by the conjugate sometimes helps. Let me show you another one kind of like that. Let's do limit as x approaches infinity of square root x to the 6th plus 5x cubed minus x cubed. And I think, so this is really similar to the previous one. You've just got an extra x cubed there, but I think I'm going to start off the same way. I'm going to multiply by the conjugate. So I'm thinking of this over 1, by the way. And then I'm going to multiply by square root x to the 6th plus 5x cubed plus x cubed over itself. I don't know, maybe this doesn't work out so well. We'll see. What do we get? So here the radicals will just cancel. The outer and inner terms will cancel. And then I'm going to have a minus x to the 6th. In the denominator, I'm going to have a square root x to the 6th plus 5x cubed plus x cubed. I think a bunch of stuff cancels. Let's see. Maybe not a bunch of stuff, but the x to the 6ths anyway. So I'm going to have 5x cubed in the numerator over square root x to the 6th plus 5x cubed plus x cubed in the denominator. Okay, now if we think about plugging in infinity, we're going to get something really large in the numerator, but we're also going to get something really large in the denominator. It's sort of like an infinity divided by infinity. And you may think to yourself, oh, well, so then that should just be 1, right? Anything divided by itself is just 1. But again, arithmetic gets really tricky when you're dealing with infinities, right? So that's not quite accurate. I think what we need to do is do a little bit more work. And I think we're in good shape because from this radical here, we can factor out an x cubed, and then we can factor out the x cubed from the entire, or sorry, in the radical we can factor out an x to the sixth. But when we take the square root of x to the sixth, it's going to come out of the radical as an x cubed. And then we can factor out the x cubed from the denominator and cancel it with the numerator. So that's my plan. So let's do it. So factoring out an x to the sixth and then taking the square root means I'm going to have absolute value of x cubed on the outside of the radical. On the inside of the radical, I'm going to have x to the sixth divided by x to the sixth is 1. 5x cubed divided by x to the sixth is going to be 5 over x cubed. And then I have this other x cubed still hanging on for dear life. Okay, since x is going off to positive infinity, x is going to be positive anyway, so I don't need to take the absolute value. Right? This is just going to be limit as x approaches infinity of 5x cubed over x cubed times the square root of 1 plus 5 over x cubed plus x cubed. Now I can factor out this x cubed, right? So I can call this limit as x approaches infinity of 5x cubed over x cubed times square root of 1 plus 5 over x cubed plus 1. And there you go. Right now the x cubes cancel. I get limit as x approaches infinity of 5 over the square root of 1 plus 5 over x cubed plus 1. Now, if we think about plugging in infinity, this thing's going to go to 0. Ooh, I get something really interesting this time, right? That goes to 0, so I'm just going to have the square root of 1 plus 0. So this is going to be 5 over square root of 1 plus 0 plus 1. 1 plus 0 is 1, square root of 1 is 1, and then 1 plus 1 is 2. So this should just be 5 halves. So you get 5 halves on that last one. Kind of interesting, right? And it goes to show you that if you just plug infinity from the beginning and you get infinity minus infinity, and you think to yourself, infinity minus infinity, that's just 0. Well, that was true for part A. It wasn't true for part B, right? We got 5 halves, actually. So that's kind of an interesting thing. I think that's all I have to say for now about limits at infinity, except just to make one last comment. You know, just like any other limits, limits at infinity may not exist. For example, think about the limit as x approaches infinity of sine x, right? That thing's not going to exist because if you think about what sine x looks like, it just alternates between 1 and -1 forever, right? It just does this forever and ever and ever. So as x gets really large, is this function going to be approaching any given value? No. Is it going to be going off to infinity or negative infinity? No. It's just alternating between -1 and 1, so the limit doesn't exist, right? So you could have that too, right? There are sometimes limits at infinity don't exist. But anyway, that's that. So that's all I have to say about 1.3. We'll see you in the next section.